Come on. All right. We are now recording. Okay, so for our warm-up, f of g of x is where you plug g of x into the f of x function for x. So instead of x squared plus 1, we have 2x minus 3 squared plus 1. When we simplify this, make sure that you multiply 2x minus 3 times 2x minus 3 to get this part here, the 4x squared minus 6x plus 9. And then you can add the 1 to it that's from out here to get 4x squared minus 6x plus 10. Then g of f of x. You plug f of x into the g of x function. So instead of 2x minus 3, it's 2 times x squared plus 1 minus 3. Distribute the 2, and we end up simplifying to 2x squared minus 1. Okay, for the second part, f of x is the absolute value function. G of x is the absolute value of 2x plus 4 minus 3. And we want to describe the transformation from f of x to g of x. And there's a hint here to be careful with the horizontal shift. So what's one thing that we can pick out that happens from f of x to g of x? What's one of the things that happens? Go ahead and type in the chat if you think you know one of the things that happens.
I have a question.
Yeah, Sean.
For the first question, wouldn't it be 4x minus 12x plus 10?
Yep, you're right. That's what you get for multiplying in your head with polynomials. 2x minus 3 times 2x minus 3, it would be twice that, so it would be 12. Thank you. Yeah, if you guys ever see something like that and catch it, please let me know. Nice job. Anyway, on the second one, anyone think they know one of the things that happened in this transformation? Yeah, down 3. There's one of them. That's probably the easiest one to pick out, right? The vertical shift. So down 3, that takes care of that part. How about the 2? What's that telling us? All right, we have left 4. That's close. That 4 does tell us that we're going left. The only problem is when we've got something in here with the x, we have to take into account what that does to it as well. And this is why I wanted to point this one out in particular, because the horizontal shift is a little tricky on this one. Let's jump over to Desmos real quick and see what happens here. Okay. We have that it's moved down 3, but it's only moved to the left 2. So where we would kind of intuitively think that it's moved to the left 4, it is actually moved to the left 2 because of what's going on with the 2 inside here with the x. So to get, if you've got some horizontal compression or stretching, then you need to factor out whatever number that is in order to tell you the horizontal shift. So if you're doing these like on a test or on a homework assignment or whatever, it's always a good idea to double check yourself by graphing, just to make sure that it's doing what you think it's doing. But anyway, if I were to factor out the 2 here, we would end up with the absolute value of 2 times x plus 2, still inside our absolute values and everything, minus 3. And this is where we can more easily identify that it's going to be moved left 2. And then it's also horizontal. Is it stretch or compression? Yes, horizontal compression. By a factor of 2. Okay. So that's part of why I did that one in the warm-up, just because I wanted to point out the case where this happens and you need to factor something out before you can get the horizontal shift by itself. Okay. Any questions from the warm-up? Anything we're not 100% sure about? Numbers we're not sure where they came from? Steps we're not sure why they happened? Okay. If you do at any point, feel free to unmute yourself and say so, or type in the chat. Anyway, so again, with things like this where you're describing transformations, it's always a good idea to graph both functions and make sure that you that they're doing what you think that they are doing, or they're doing what you have written down. Anyway, today we're talking about inverse functions. It's 1.7. Determining if a function has an inverse by examining the graph, and then once we've determined whether or not it has one, finding the inverse. Okay, so this should sound a little bit familiar, at least from Advanced Algebra Trig, hopefully. It is a review of exactly that. We're going to talk a little bit more about the domain of an inverse. Okay, so grab your notes if you don't have them out already from the warm-up. And here we go. (1.7) inverse functions. Okay. So the first thing we need to know about inverses is how to decide if a function has an inverse or not. And so in order to determine if it has an inverse or not, there's something called the horizontal line test. So you've heard of the vertical line test to determine if something is a function or not. Horizontal line test tells you if it has an inverse or not. And it's the exact same idea. So the horizontal line test is stated as a function has an inverse function if you can draw a horizontal line anywhere on it, and it intersects the function only once. Okay. So this concept of the horizontal line test illustrates something called one-to-one correspondence. Which basically means that each x value matches up with only one y value and vice versa. So each x value and y value are a pair. And there's not y values that are attached to multiple x values, and there's not x values that are attached to multiple y values. Okay, so for example, if we have something like y equals x squared. What do we think? Does that thing pass the horizontal line test? Well, probably not, because I can draw, a line right there. Thanks, guys. I can draw a line through there and cross the function twice. In fact, you can draw a line through just about anywhere horizontally on this function and intersect the function more than once. So that just tells us that this has no inverse function. But if we've got something instead, like y equals x cubed, that passes the horizontal line test. So this one does have an inverse function. Okay. So that's a simple way to determine whether or not it has an inverse. Now we're going to deal more with actually finding the inverse. Okay. And for people who enjoy steps, finding inverse functions is a really something that lends itself well to going step by step. So if you enjoy steps, this is a great topic for you. So here we go. I'll list out the steps and then we'll kind of go through the steps on one of them. The first step is to change f of x into a y. Just because it makes our lives easier when we're going through and solving things. Step 2, swap x and y. So we're going to have them trade places completely. Okay. And then there's kind of a step 2.5 here. Step 2.5 is to find your new domain restriction before you start solving. Because that's the easiest place to do that before you actually start solving for y. Because step 3 is to actually solve for y, because that'll give you the inverse function. Then step 4, at the end, we're switching it back into function notation. So switch y to f inverse of x. This is the notation for f inverse. So f to the -1 is what it looks like. So those are our steps of finding the inverse. Give everyone a moment to write that down if you would like to write that down. And then we'll do a couple examples. Okay. So in my examples, I'll show a couple with easier to find domains, and I'll show a couple with more difficult to find domains. That way we kind of cover the whole spectrum here of what we need to do. Okay, so first example, we're going to start with f of x equals x cubed plus 5. Okay. F of x equals x cubed plus 5. So step 1, make the f of x into a y instead. Step 2, swap x and y. So instead of y equals x cubed plus 5, it's going to be x equals y cubed plus 5. All right, and then before we start solving, we want to figure out what our new domain is going to be, because sometimes at this step, we can be, so we know that the domain is the x values, right? So while we have x equals here, we may as well figure out if there's going to be any x values that it would not work for. And oh, there's a dog. Okay, sorry, distractions. Very cute distraction. Okay. So finding the new domain restriction before solving. In this case, this could be any value from negative to positive infinity. There is no restriction on the domain for this particular one. There's not something here that could not be made from y cubed plus 5. The cases where you'll find a domain restriction is where you end up with like 1 over y plus something, or if you end up with like the square root of y plus or minus something. Those will be cases where you have domain restrictions. This is one of the cases where our domain is going to be just the implied domain of negative to positive infinity. So that's good. So from here, our domain is going to be negative infinity to infinity. Now we need to start solving for y and get y by itself. So what I would do first here is subtract 5 on both sides so that we get x minus 5 equals y cubed. And then to undo a cube, you just take the cube root. And so we get the cube root of x minus 5 equals y. And then lastly, we want to change the y into f inverse of x. And I'm going to put it over here. So we have f inverse of x equals the cube root of x minus 5. And it's good for this domain. So there's no restriction on the domain for that particular inverse. Okay. So that example was a bit on the simpler side. It had a nice domain. It had only a few steps. Any questions on that one? Any steps we're not sure why they happened, or numbers we don't know where they came from? Okay. If we do at any point, please say something. I'm going to put my next example next to this one. All right, this one's going to be a slightly, it's going to have a domain restriction in it. Let's just say that. F of x equals the square root of x plus 3 on the outside. Okay, so same deal here. Change the f of x into a y. And then swap the places of x and y. Okay, so here's where we end up with a bit of a domain restriction. Because are there any values here that y couldn't be, or the square root of y? Is the square root of y ever going to be a negative number? Yeah, exactly. Negatives. Right. So the square root of y is always greater than or equal to 0. So then this entire side, the smallest that it could be is 3. Because 0, the smallest that this can be is 0. And 0 plus 3 is 3. So that tells me that our domain, the smallest value on the domain is going to be 3. So 3 to infinity will be our new domain for whenever we get our inverse. That'll be the domain of the inverse. Okay. So that's how we would determine the domain for our inverse if it's going to be restricted. Okay. Now we can go through and solve. So solving, we would subtract 3 from both sides and get x minus 3 equals the square root of y. And then to undo the square root, we can square both sides. So we get y equals x minus 3 squared, which means our f inverse of x is x minus 3 squared on the domain 3 to infinity. Okay. Now we might be going, okay, why do I need to restrict the domain here? This doesn't have any domain restrictions. I can plug in anything for x and square it. You know, that's fine to do. Would you simplify this? You could. If we're talking inverses, you can leave it if you would like to. I'm okay with you leaving it like this. Or you can simplify a good point. You can go x squared minus 6x plus 9 if you'd like. But yeah, we might think, okay, this doesn't have a domain restriction. It only does because the original form of it, the original form of the inverse has a domain restriction. So before we solved and put it in a nicer format like this, there was a restriction on the domain. So that's why. Anyway, there's our answer. And I believe the IXL version of this topic is okay with you leaving it like this as an answer as well. If you find that it's not, you can always simplify it like this, but I'm like 99% sure that it's okay with leaving it like this. And I'm also okay with you leaving it like that. Okay. Anyways, let's see. Let's have you guys try one. This time f of x equals the square root of 2x plus 1. Go ahead and try finding the inverse and any restrictions to the domain. And when you think you've got it, type down in the chat. As you finish, if you would like to check your work, I do have it worked out. All right, for those of you who are done, what did you say for the restriction on the domain? What are the values that this can be? All right, Mitchell says 2. Anyone else get something that you would restrict the domain? Thinking about x values of the domain, is there anything that this square root of 2y plus 1 won't end up being? For example, is a square root of 2y plus 1 ever going to be less than 0? No. Right, so this whole side here will never be less than 0. It's always going to be greater than or equal to 0. So that means that my domain is always going to be greater than or equal to 0. So my new domain is also going to be 0 to infinity, or you could say x greater than or equal to 0. Those would be the same thing. Okay, so that's our domain restriction there. Any questions on that one? Any numbers we're not sure where they came from, steps we're not sure how they happened? Okay, then we'll talk about one more, or at least one more. Let's see. There's a few things that I want to make sure we mention. We're going to do the inverse of f of x equals 4 over x. Let's see what that looks like. So let's go through that one. So we do y equals 4 over x, so then switching them, x equals 4 over y. And pausing here, is there anything that this number will never be? Will this number ever become 0? Yeah, exactly, Jasmine. This number will never be 0 because as big as you make this denominator, it will get very, very close to 0, but it will never actually be 0. So here's a restriction on the domain. X will not be 0. Okay. So then we continue solving for y. I'm going to multiply by y on both sides. So we get y times x equals 4. Then I would divide by x on both sides to get y equals 4 over x. So f inverse of x equals 4 over x. Wait a minute. Isn't that the same as our original function? So this function is its own inverse. So that's kind of an interesting thing. And it's interesting to look at graphically as well. So we're going to take a look in Desmos real quick at what that looks like. So we had 4 over x was our function, and it's also its own inverse. So when we're taking an inverse, you know, the fact that we switch x and y and then solve, that's kind of also symbolic of what's happening to the coordinates and stuff like that. X and y are switching. And when x and y are switching, if you remember from way back in geometry, when you switch x and y, that's also known as reflecting over the line y equals x. So there's the line y equals x. And a function is its own inverse when it's symmetric with respect to that line y equals x. So when you can fold it and have this side match up with this side perfectly along this line, then you have something that is its own inverse. So I just thought that was interesting to point out. So anyway, you can have a function that is its own inverse. So if you get something like that, you know, you didn't do anything wrong. It's just that's how that function behaves. Okay, I think that is everything that we needed to do for today. Let's see, any questions at this point? Any general ones or any numbers we're not sure where they came from, steps we're not sure why they happened? Okay. If you do, feel free to unmute yourself and say so. Otherwise, I'm going to post the assignment. Today's assignment, you have two choices. So whichever one, if you're sick of IXL, then your two options are a worksheet or an IXL. So if you're sick of IXL, maybe do the worksheet. If you learn better from IXL, maybe you do the IXL. Hey, good job, Aiden. Okay, so looking at this. Here we go. The worksheet is the 1.7 worksheet right here. It's got 15 questions on it. They're all about, let's see, determining whether something has an inverse, and then if it does, finding the inverse. Or there are two questions in the middle asking you to show that these two functions are inverses of one another. One way that you can show that is to find the inverse of one of the functions, and if it's equal to the other one, well, then they must be inverses. So that's what I would do if I were you for 9 and 10. Or you can do IXL. It's A16 in pre-calculus. And it's all about just finding inverse functions and doing exactly what we've been doing. Keep in mind for both of these, you're going to need to find any domain restrictions. So we're still practicing with that. But yeah, now you have the assignment. If you feel good about it, feel free to head out and work on the assignment. If you have questions, feel free to stick around or pop back in and out as you have questions. There will be an exit ticket towards the end of class. Yeah, have a wonderful day.